Good morning, students, and welcome to this morning's class. Today, this morning, we'll be continuing our discussion on the topic Chebyshev's inequality. Chebyshev's inequality. Chebyshev's inequality. Do remember that in our previous class, we did say that Chebyshev's inequality is an upper bound probability, and it is equally a probabilistic inequality. What does it do? It provides the upper bound probability that the absolute deviation of a random variable, say x, from its mean will exceed a given threshold. I repeat, what does Chebyshev inequality do? It provides the upper bound probability that the absolute deviation of a random variable, say x, from its mean mu will exceed a given threshold. How do we write this inequality that I have just defined in a statement or in a sentence? It is written this way: that the probability of absolute value of a random variable x from its mean mu will be greater than or equals to k, standard deviation, will be less than or equals 1 all over k raised to power 2. This is what is called Chebyshev's inequality. And then this inequality is read this way: that the absolute deviation of a random variable x from its mean mu being greater than or equals a given threshold measured in standard deviation, k standard deviation, is less than or equals 1 over k raised to power 2. That is how to read this inequality. Of course, in that our class, we did say that this inequality has another variation, which of course means the same thing. Because the interest in this one is that this absolute deviation of a random variable x from its mean mu will be greater than or equals k standard deviation. What if the interest is that the absolute deviation is strictly less than k standard deviation? How do we redefine this inequality to suit this definition? It will be given this way: that probability, the absolute value of x from its mean being strictly less than k standard deviation should be greater than or equals 1 minus 1 all over k raised to power 2. Watch the variations that we have at the right hand side. What I have here is 1 over k raised to power 2. What I'm having here is 1 minus 1 over k raised to power 2. This variation is as a result of this change in the inequality sign. Here is greater than or equals. What I have here is 1 over k raised to power 2. But here is less than, which is 1 minus what we have here. The two equations that we have on the board are called the Chebyshev's inequality. Of course, stating them on the board for our students to see and be able to recognize is important. But the focus of our today's class is to be able to drive these Chebyshev's inequalities with our students, so that they will be able to know everything about the theory of the inequality. And do remember that in our previous class, we did say that the Chebyshev's inequality can be derived using two approaches. The first approach is, 1, the Markov's inequality approach. Markov's inequality approach. And then we have what we call the conditional expectation approach. Conditional expectation approach. So these are two approaches that one can use to be able to come up with these Chehyshev inequality. We also mentioned in that class that our discussion on Chebyshev's inequality will be centered on the Markov's inequality approach. So our discussion today, this morning, on Chebyshev's inequality will be centered on the arms of Markov's inequality approach. So you are going to permit me to clean the board, then we now write the Markov's inequality, and then use the approach now to drive the Chebyshev's inequality. What do we want to drive? We want to drive this formula. And this formula says, or this inequality, and this inequality says, let me put it this place, the probability, the absolute value of a random variable x from its mean mu greater than or equals what? K standard deviation, then will be less than or equals what? 1 all over k raised to power what? 2. This is our interest. That's what we want to drive. So you permit me to clean this side, then now write the Markov's inequality approach, and from there we run down the proofs together. Thank you very much. So we are now talking about the Markov's inequality approach. Markov's inequality approach. And one thing I need to mention before we progress is that in our previous class, when we mentioned the two approaches through which one can obtain the Chebyshev's inequality, we concentrated discussion on the Markov's inequality approach or Markov's inequality in our previous class, which of course began by stating the Markov's inequality and as well proving the Markov's inequality. Therefore, if you are just joining us this morning where you did not partake in that previous class, we might have to recommend that class to you to ensure your deeper knowledge in what we are discussing today. So if you have not watched the video, I encourage you to watch the video to, of course, enhance your understanding of what we will be discussing this morning. So I have the Markov's inequality approach. How do we state the Markov's inequality? Since we are going to use his approach to discuss the Chehyshev inequality. The Markov's inequality is stated as that the probability of a random variable x being greater than or equals what? A is less than or equals what? E of x all over A. Where this A is a positive quantity and this x is a positive random variable. That is a random variable that takes on only positive values. That is the probability that a random variable greater than or equals what? The positive value what? A should be less than or equals expected value of that random variable x all over what? A. Okay? What if now we decide, in as much as this x is a positive quantity, what if we define the quantity this way? We say let x minus what? Mu all raised to power 2 be a positive quantity. Of course, you know that whenever you say anything minus anything raised to power 2, definitely it is going to turn into a positive quantity because of this square that is what that is here. So we are now saying let x minus mu raised to power 2 be a positive quantity such that we can apply this Markov's inequality to that quantity since it is a positive quantity. So we are now going to apply this Markov's inequality to this positive quantity, just as x was a positive random variable. And then we do that together. So what I had here was what? P I'll write P, I'll open what? A bracket. What I had here was x, which is the positive quantity. But what we are talking as being a positive quantity is this. So what I have here becomes what? X minus what? Mu, all raised to power what? 2. Here is greater than or equals, greater than or equals. Here is what? Is my A. I'll close the brackets. Here is less than or equals, less than or equals. Here is expected value, is expected value. Expected value of a random variable x is a positive quantity. Look at our positive quantity here now. So open a bracket, x minus what? Mu, all raised to power 2, close the quantity, all over what? Over A. We can decide to say, let A equals what? K raised to power 2, sigma raised to power 2. We can decide to say something like this. So by implication, wherever place I see A, I am going to substitute with K raised to power 2, sigma raised to power 2. This is the definition, of course. Once you define something, you apply it within the context of what you are proving. So here becomes what? P. Here is this way. Open x minus what? Mu, all raised to power 2. Here is greater than or equals. I won't write A again. I'll write K raised to power 2, sigma raised to power 2. K raised to power 2, sigma raised to power 2. I'll close it. This is less than or equals. Here is my E. I'll open. Here is what? X minus what? Mu, all raised to power 2. You close it. All over K raised to power 2, sigma raised to power 2. That's what we have there. Okay? And of course, you should know very much well that for this quantity, x minus mu raised to power 2, to be greater than or equals k raised to power 2, sigma raised to power 2, implies that absolute value of x minus what? Mu must be greater than or equals what? K, sigma. If this must be greater than or equals this must be 2. And in that case, I can use this in place of this. Using this in place of this, what I'm now going to have becomes, here is my P, I will have my P. I will now open here the way it is. The whole of this I'm going to replace with this. So absolute value of x minus mu greater than or equals what? K, sigma. I'll close it. Is now less than or equals what? E of what? X minus mu all squared, you close it, all over k raised to power 2, sigma raised to power 2. Okay? Now, I want you to look at what you have here. What you have here is expected value of x minus mu all raised to power 2. You should know that this is variance in statistics. In fact, this is the variance of the random variable x everywhere. So in that case, I can write this in this way. Permit me to call up what I have here. I can write this in this way. Here is my P, which is what I have here. So I'll open a bracket this way. Here is my absolute value of x. Here is minus mu, minus what? Mu. Put it this way. Here is greater than or equals, greater than or equals. Here is k sigma. Here is what? K sigma. Close it. It's less than or equals. This quantity on top is already variance. So I have what? Sigma squared all over. What I have here is k squared sigma squared. I have what? K, or I have what? K squared sigma squared. I have sigma squared here, I have sigma squared here. This can cancel this. And I'm left with what? P, absolute value of x minus mu, greater than or equals k what? Sigma is less than or equals, here is what? 1 all over. Here is what? K raised to power 2. You have proven the Chehyshev inequality. Look at what we have here. Look at what we have here. So this is how to go about the proof of the Chehyshev inequality. Now, equally, permit me to clean this board. See what we have done from here to here, which I want to believe is not confusing. If it's confusing anywhere, drop your comment in the comment section. Once we come across it, we come to your rescue. Now, we are going to click from here down and make another definition so that when you are going through the pages of textbooks and you see what looks like a variation of the Chehyshev inequality, you now really know the angle they are coming from. Because at times you see a Chehyshev that doesn't contain what? This sigma here. You just see something like what? Like K. How are you going to see it in that perspective? So permit me to clear here. Let us make a definition that will go towards that direction. So I will now clean here. Permit me to clean here. Well, somebody else can say, you say let A equals K raised to power 2. Ab initio, I said let A be sigma square K square. Here I'm saying let A be K square alone. So in that case, anywhere I see K, I will put K squared. So here becomes what? P. Here is x minus mu all raised to power 2 greater than or equals. Here becomes what? K raised to power what? 2. I'll close it. Less than or equals what? E. Here becomes x minus what? Mu all raised to power 2 all over K raised to power what? 2. See what I now have here in this case. Then we now know, of course, that for this condition to hold, that x minus mu raised to power 2 is greater than or equals K raised to power 2 implies that absolute value of x minus what? Mu must be greater than or equals what? K. So in that case, I can use this in place of this. So what I now have here becomes what? P. I'll now open a bracket this way. Here is x minus what? Mu greater than or equals what? K. Close the bracket. Less than or equals, here is what? E of x minus what? X minus what? Mu all raised to power 2. Close it. All over K raised to power what? 2. Of course, like I had earlier said, what we have at the numerator is the variance of the random variable x, which of course is sigma. So you can write this now to be, here is my P, I have P, absolute value of what? X minus what? Mu, greater than or equals what? K, is less than or equals, here it becomes, the whole of thing that I have here now is what we call sigma squared. So here becomes what? Sigma squared all over K squared. So this is another Chehyshev inequality you can see. The only difference you are seeing, the difference between this and this, that in this case, in this very case here, you have K sigma. Here, you have that your sigma is 1. If your sigma squared is 1 here, if this sigma is what? Is 1. 1 times K is still K. If you bring that 1 here and say 1 squared, it still returns this 1. You have K squared, you have K squared. So the only thing here that here you are saying that this your sigma should be 1 for you to have this thing here. And if that sigma is 1, definitely now you can have this thing now to be P x minus what? Mu greater than or equals, this sigma is being 1. So what you have here is what? K less than. This sigma here is being 1. So you have 1 over K raised to power 2. Which is this? Which is this? So that is how to prove the Chehyshev inequality. Thanks for your audience thus far. But then another thing I want to remind you is the proofs which we have just done on the board. We are not concerned whether the random variable x is a discrete random variable or whether it is a continuous random variable. So we are now going to prove the Chehyshev inequality from the approach that the random variable x here is continuous, and equally prove it now that it is what? Discrete. So permit me to clean the board while we now go through that thing quickly before we begin to take questions. Permit me. Okay, let's go together. First of all, we are looking at x as a continuous random variable. First of all. And in that case, remember the definition we gave before. We began by saying let x minus what? Mu all raised to power 2 be a positive quantity. In that case, you can say that this sigma, because this, of course, if you write this way, you now have that my sigma squared is expected value of this random variable, which is what? X minus what? Mu all squared. This equals, if you want to write the expected value of any random variable x, you now say it is integral over the range of x, okay? Then here is the positive quantity which we have, so it is now going to be x minus what? Mu all raised to power 2 f of x dx. So this is variance, sigma squared, which can be expressed like this, which can be expressed like this. We want to actually know the true range of this x and be able now to partition it because, of course, if x is a continuous random variable, we can easily say from minus infinity to positive what? Infinity. We want to partition this range, which begins from minus infinity to positive infinity. And let us look at this partition here. Let me say I have something like this. Then I have equal to something like this. Look at what I have. Let this center here be mu. Then let from here to here stand for mu plus k standard deviation. And then let from here to here stands for what? Mu minus k standard deviation. Let here be minus infinity. Let here be positive infinity. So these are the partition of this minus infinity to positive infinity. Which means integrating this quantity from minus infinity to positive infinity is the same thing as integrating this quantity from minus infinity through mu minus k standard deviation down to mu plus k standard deviation down to positive infinity. So let us do the integration together with you. So meaning that this my sigma squared, this my sigma squared, which is this, is equals. Let us first of all integrate from minus infinity to this. So I have integral from minus infinity to what? Mu minus k standard deviation of this quantity, which is what? X minus mu all raised to power 2 f of x dx plus. Let us integrate from this to this. So you have integral from mu minus what? K standard deviation to mu plus k standard deviation of this quantity x minus mu all raised to power 2 f of x dx. Let us now integrate from here to here. We now say plus integral from now mu plus k sigma to infinity proper, positive infinity of this quantity, which is x minus what? Mu f of x dx. This and this mean the same thing. And what we are saying is what you have at the left and what you have at the right are the same thing. So if you subtract anything from the right, the left will be greater. I want to drop this quantity at the center. If I remove this quantity at the center, it means that this quantity I have here now should be greater. Okay? And in that case, what I'm now going to have is, you permit me, of course, you know where we started from here. In fact, let me bring this in closer to enable me divide the word to the board. Let me bring this in closer here. What we are having here is, we are saying, let our sigma raised to power 2 be e of x minus mu all raised to power 2, okay, all raised to power 2, which is the same thing as integral from minus infinity to positive infinity of x minus mu all raised to power 2 f of x dx. This and this are the same thing. So I want to drop this quantity at the center. If I drop it, this thing will be greater than or equal to that. So I will now have, therefore, sigma squared is greater than or equals, here I'm saying strictly equals. But because I'm going to drop this thing at the center is greater than or equals, I will pick this. Integral from minus infinity to mu minus k standard deviation of x minus what? Mu all raised to power 2 f of x dx plus. I'm dropping this coming over here. Integral from mu plus k standard deviation to positive infinity of x minus mu all raised to power 2 f of x dx. This is 2. Okay? Then I really want to know what this x minus mu all raised to power 2 means. But there is something I want you to see. You know our interest from here to here means x is less than this quantity. And our interest from here upwards means that our x is greater than this quantity. So here, x is less than this because it is from minus infinity to this. So x is less than this. From here, it is from here to here. So x is greater than this quantity towards to infinity. So meaning that if I come here, I can say that for this one, my x is less than or equals this quantity, which is mu minus k standard deviation. And of course here, my x is greater than or equals to what? Mu plus k standard deviation. So in that case, I can bring in this mu over here. I have what? X minus what? Mu less than or equals minus k standard deviation. Here I am going to have x minus mu greater than or equals what? K standard deviation. If you watch, this one contains minus, but this one contains what? Positive. See the sign here, less than or equals to. See the sign here, greater than or equals to. If you square both sides of this, you'll be able to reconcile this inequality sign. Because that square will take care of this negative sign. So squaring both sides now, what you are going to have now becomes what? X minus what? Mu all raised to power 2 is greater than or equals to what? K raised to power 2 sigma raised to power 2. Here is still the same thing, x minus what? Mu all raised to power 2. If now be greater than or equals to what? K raised to power 2 sigma raised to power 2. And if you want, what I have here is x minus mu all raised to power 2. So I am free to use in place of x minus mu all raised to power 2 these quantities and these quantities. So I will now come here and say, therefore, this my sigma raised to power 2 greater than or equals, I have what? Integral minus infinity to this. I have minus infinity to mu minus k standard deviation. I will write this quantity again. I will write this, which is k raised to power 2 sigma raised to power 2. I have what? F of what? X dx plus. Here is what? Integral mu plus k sigma up to positive infinity. I will now write this quantity k raised to power 2 sigma raised to power 2 f of what? X dx. Okay? You know where we started. So permit me to clean here. I believe you are taking note of what we are doing. So permit me to clean here. Let us continue this approach down. So I'll clean here. You know where we started. We started by defining this to be this, to be this, to be this. So this equals this plus this plus this. We dropped off this one and then decided to say it's greater than or equal to, making use of only this and this. So permit me to clean this place from this diagram so that we can complete our proofs. Okay. So when we now come here now, of course, k raised to power 2, sigma raised to power 2 are constants. So I can decide to divide all two with that constant. And dividing all two by constant, what I'm now going to have is what? Sigma raised to power 2, which is this one, all over. I'm dividing 2 with this. So I have k raised to power 2, sigma raised to power 2, greater than or equals to. I have integral from minus infinity to mu minus k standard deviation. Dividing through will cancel these ones here. So what I have left is what? F of x dx plus integral from this mu plus k standard deviation to positive what? Infinity. Dividing all through will cancel this. So I have f of x dx. That's what I have there. So, and of course, you know that f of x dx is talking about a probability value. Integral of this to this is a probability value. Integral of this from this to a probability value. And you remember one thing. That one thing you need to remember that we earlier had defined that from here to here, our x is less than or equals what? Mu minus k standard deviation. And from here to here, our x is greater than or equals to what? Mu plus k standard deviation. Okay? So if you bring this mean here, you have x minus what? Mu. This way and this way. So you now have what? Less than or equals what? Minus k standard deviation. Here is x minus what? Mu. This way, this way. You have what? Greater than or equals what? K standard deviation. So you can actually make use of an absolute value if you must reconcile this quantity, this negative sign, and then this inequality. You can make use of absolute value. And if this is less than or equal to minus this, and this is greater than or equal to this, it implies that absolute value of x minus what? Mu is greater than or equal to what? K standard deviation. If this is this, and this is this becomes what? True. So actually, from here to here, what you are trying to get is this probability. Probability that absolute value of this is greater than this. So I'm going to remove the whole of this and replace with this because that's actually what you're trying to get here. So what you now have becomes what? Sigma raised to power 2 all over k what? Sigma all over k squared, sigma squared is greater than or equals, here becomes probability absolute value of what? X minus what? Mu is greater than or equals what? K standard what? Deviation. And remember that this is sigma squared, this is sigma squared. So this is 1 and this is 1. Then what you now have here becomes, what you have here is what? P, absolute value of x minus what? Mu, greater than or equals what? K, standard deviation, is less than or equals, look at it, greater than or equal to, greater than or equal to, less than or equal to, less than or equal to 1 all over k raised to power 2, which is what we had here. Which is what we are trying to prove. Look at it here. Look at it here. Okay? If you want to do that of what? Of a sum, I'm just going to give you a hint about that of a discrete random variable. Because in a discrete random variable, what is implied that anywhere you see integral, you replace with what? With sum. So I will now show you how to go about that one, while you might try to complete it to see whether we'll be able to arrive at this. So if they ask you to drive the Chehyshev inequality, of the upper bound of the random variable what x. Taking these what values from the approach of a continuous random variable, you follow this thing which I have done and you arrive at what at this. Thank you very much for your audience. Let me clean the board and show you how you go about that of summation to see whether you are going to arrive at the same thing. So permit me to clean this board. Okay, here we still make that our definition before. Definition we are saying that we are making is that let our x minus mu all raised to power 2 be a positive random variable. We normally make that definition such that we now have that our sigma raised to power 2 is equals expected value of x minus mu all raised to power 2. This time around, it is not a continuous random variable. It is a discrete random variable. So it is not going to be integral over the range. It is going to be sum over the what? Over the range. Okay? So it's actually going to be sum. So you have sum, okay, over the range of what? Of x. Okay? Then you now have this x minus what? Mu all raised to power what? 2. So you now have this summation of this all raised to power 2. You now have what? P of what? Of x. P of x. Okay? Now let us equally talk about partitioning the range of this x. Like we did before, partitioning them this way, as usual, having here to be mu, having here to be what? Mu minus k standard deviation, having here to be what? Mu plus k standard deviation, having here to be minus infinity, and having here to be positive infinity. So in that case, you now come summing this quantity over this what? Range of x. We have partitioned this our range of x now to be this. It's the same thing as summing this quantity over all this. So which means it is now going to be this our sigma what squared is now equals. You have sum which begins from minus infinity to this. So you have minus what? Infinity to what? Mu minus k standard deviation of this quantity of x minus what? Mu all raised to power 2 p of x plus. You sum from here to here, which is sum from what? Mu minus k standard deviation to mu plus k standard deviation of x minus mu all raised to power 2 p of what? Of x plus. You sum now from here to here. So sum from mu plus what? K sigma to positive infinity of x minus mu all raised to power 2 of p of what? Of x. As usual, drop the one at the center to enable you use greater than or equal to. You have sigma what? Squared greater than or equals. You now have sum minus infinity to mu minus what? K sigma of what? X minus what? Mu all raised to power 2 p of what? Of x plus. Come here. Sum of what? Mu plus k sigma what? Plus k sigma to what? Positive infinity of x minus mu all raised to power 2 p of x. You have something like that. Okay? When you have something like this, just like what we said before, you now begin to ask yourself a question. The question you are going to ask yourself is, from here to here, our x is less than this point. That's why you started from minus infinity to this. So x, for this place, for this sum, x is less than this quantity. But for this sum, x is greater than or equal to this quantity. Here, x is less than or equal to this quantity. So you have here that x is less than or equals to what? Mu minus k sigma. And here you have that x is greater than or equals to what? Mu plus k sigma. You know this. So if I bring this over here, I have x minus mu this way, being less than or equals minus k sigma. And here is x minus mu being greater than or equals what? K sigma. Now, if I must reconcile this inequality sign, I should square both sides of the quantity. So I'm squaring them will now tell me that x minus what? Mu all raised to power 2 should be greater than or equals what? K raised to power 2 sigma raised to power 2, which of course is the same thing here. Here is x minus mu all squared greater than or equals k raised to power 2 sigma raised to power 2. At that point in time, you return back here. Anywhere you see x minus mu raised to power 2, you put this quantity, put this quantity. And what you have there becomes what? Sigma squared greater than or equals what? Summation from minus infinity to what? Mu minus k sigma. What you are putting there here now becomes what? K raised to power 2 sigma raised to power 2 p of x. P of what? Of x. Then what you're now going to have here is now plus. Summation here becomes what? Mu plus k sigma to positive infinity of this quantity k raised to power 2 sigma raised to power 2 p of what? Of x. So this is a constant, this is a constant. You can divide it all through. Dividing all through will now make you to have that you now have what? Sigma what? Squared all over k squared sigma squared is greater than or equals here. You now come here. This is summation minus infinity to what? Mu minus k sigma of, you have this thing dividing through k squared sigma squared dividing each quantity here too. Will now cancel off this and cancel off this. So what you are just going to have here is what? P of what? X. So plus. The same thing applies here. You have summation of mu plus what? K sigma, then to positive infinity of what? P of x. And if you remember that thing we said, you are summing probability from here to here, plus summing probability from here to here. You understand? So it's as good as what we already had said the other time, that from here to here is probability, absolute value of what? Of x minus what? Mu is greater than or equals what? K sigma. We already showed it before. It doesn't change. Sorry? So what we now have here now becomes that this is what? Sigma squared all over k squared sigma squared is greater than or equals what? P of this x minus mu greater than or equals what? K sigma. And then this will cancel 1. This will cancel this. And you have this to be this, which is what we proved. Let me take the cover of my marker, which is exactly what we had before. So this is how to go about proving the Chebyshev's inequality. As we began by looking at the Chehyshev inequality without paying attention whether our x is a continuous random variable or whether it's a discrete random variable. At the end of which now we decided to look at proving it now when x is continuous and then when x is what? Is discrete. So permit me now to wipe the board. Let us take a few questions from what I already have down here. So permit me to clean here. These things are not difficult. Once you go through it now, you can try to see whether you can prove it by yourself. Remember to subscribe to our YouTube channel, like, share, and comment on our videos. Thank you very much. Let us look at few questions here. Let us look at few questions. Okay? The first I have here says, number one, I will target worked examples. Worked examples. So number one, they say let x follow a uniform distribution, uniform with parameters 0 and what 4, or with interval, okay, with interval 0 to 4. They say find the Chebyshev's upper bound. The Chebyshev's bound for the probability. The Chehyshev bound for the probability. P, absolute value of x minus mu being greater than or equals to what? 1. They ask us to do this. So let's solve together. So as a way of solution, you say solution. First of all, transform this thing to look at what we proved earlier. If you watch now, we are not seeing anything like K sigma here. We are seeing something like 1 here, which we can just take as whether it is the sigma or whether it is K. That was the essence of proving the other one that ended with what? K, and the other one that ended with K sigma. So first of all, transform this into what you know. You know that Chebyshev states like this, that probability that x minus what? Mu greater than or equals to what? K is less than or equals to what? Sigma squared all over k raised to power 2. You remember this. So first of all, transform this to look as this. So if you transform this to look at this, what you are going to have is this. And this sigma square, of course, is the variance of this x. So it is just good as var x. So you can write as what? As var x, which of course is equals to what? var of x all over k raised to power 2. So you can write this in this way. So if I transform what I have here, I will say therefore, my p, absolute value of x minus mu, being greater than or equals to 1, I'll close. Here is less than equals, here is my var x. So I'll write var of x, this x, all over. Here is my k, I have k raised to power 2 here. That's why I have k raised to power 2 here. But here is 1, so I have what? 1 raised to power 2. And 1 raised to power 2 doesn't change anything. So it is just what? var of what? Of x. Because of that, you now come back here. Come back here. So you'll be able now to get for yourself the variance of what? Of x. And for you to get the variance of x, what you are going to do is this. The var of x, you now say but var of x is given as b raised to power 2 minus a raised to power 2 all over what? 12 for a uniform distribution. For a uniform distribution. And what you are referring like what? A, your b is this 4, and this your a is this 0. So this is given as you have 4 raised to power 2 minus 0 raised to power 2 all over what? 12. Which of course will now give you what? 16 all over what? 12. Because 4 raised to power 2 is 16, 0 raised to power 2 doesn't change anything, all over 12. Something can go in. 4 can go into this to give me 4, and 4 can go into this to give me what? 3, I guess. 4 over what? 3. So we now say therefore, what you have here is what? P, absolute value of what? X, minus what? Mu, greater than or equals what? 1, is less than or equals var x. Less than or equals what? Var x. Less than or equals var x, which is equals 4 over 3. Which is equals 4 over 3. That is if that is not really the upper bound of that, giving us 4 over 3. We really need to reconcile certain things here to see if this is truly right. To see if that is truly right, we need to first of all look at certain things. Reason, we are going to revisit this thing to know whether this is very right. Because I'm seeing this as 4 over 3, and then 4 over 3 is not a probability value. This is going to give us a 1 point something thereabout. So we are going to revisit that particular problem and then know exactly what is meant by that statement. Okay? So permit me to clean this. We have already promised you we are going to look at something with regards to this. So permit me to clean this. Okay, let us take another number, uh, which is number 2. We promised you are going to look at that number 1 together. This is number 2. Number 2 says, let a random variable x be such that e of x equals 1 and var of x equals what? 1 equally. They say find the Chehyshev upper bound. Find the Chehyshev upper bound to the probability that p of x is greater than or equals what? 3. That's what they want you to do here. Okay? That a random variable x is defined such that expected value of that random variable x is 1 and its variance is what? Is 1. So they now ask you, find the upper Chehyshev upper bound of the probability p of x greater than or equal to what? 3. The effort you are going to do first of all is to transform this into what looks like what? Chehyshev. And first of all, you remind yourself your Chehyshev. The Chehyshev, of course, you know, says that the probability absolute value of x minus what? Mu greater than or equals what? K is less than or equals what? var of x all over what? K raised to power what? 2. Always remember this. Okay? Now, in that case, you move. Your moving is, if you come to this problem, you are given p of x greater than or equals what? 3. How do I transform this to looking like this? Of course, this mu here means expected value, which is the mean. And the mean of it is given as what? As 1. So what you are going to do now is, this is now equals. This implies that this is probability absolute value of this my x minus. Here is x. I am saying minus what? Mu. Okay? Is greater than or equals, I'll come to this 3. Because I subtracted the mu here, I must subtract mu here. Greater than or equals what? 3 minus what? Mu. Close it. Less than or equals what? var of x all over k raised to power 2. But we are told that our mu is what? Is 1. And our var is 1. So this becomes p absolute value of x. Here is what? Minus what? Mu. Greater than or equals, here is 3. Here is mu. And mu is 1. 3 minus what? 1 is what? Is 2. Close the bracket. Less than or equals. Our variance is equally given as 1. 1 all over k raised to power 2. If you watch this, it looks like this now. And looks like this. Okay? Now you equally go ahead. Now what you have here is less than or equals to var of k raised to power. Okay, what I had here, all over var of what? Of x. Now I don't need to put this is less than or equals var of what? Of x. Because I'm here to get, look at my k here. It is just now that I got what my k is. It's just now that I got what my k is. So it's as good as first of all cleaning this thing. Sorry. It's as good as first of all cleaning this thing. First of all, cleaning this thing. And then from here, we arrive at this together. Okay? So from this, we arrive at this together. We now look at this and look at this. They are now the same thing. We now see how we can change it now into what is here. So we now say it's less than or equals, here is my var of x. Var of x. Here is my k. K is now squared here. Here is my 2. 2 will be squared here. So I have 2 what squared. So this becomes p of x minus mu greater than or equals what? 2 less than or var of x is 1. You have 1 all over. 2 raised to power 2 is what? Is 4. So which means that is equals 1 over 4. So the upper bound, the Chehyshev upper bound probability of this is given as a 1 over 4. First of all, pick this, transform it to look at what you have here. Once it looks at something that you have here, you now bring in your right sign, which is this, and you arrive at that. Thank you very much. Permit me to clean the board. Let us equally take another question. Okay, let us take another question before we now say that we have done some good work. This question says, and I write, okay, you say number 3. Let x follow exponential with parameter of 1. With parameter of what? 1. Okay? You say find the Chehyshev upper bound. Find the Chehyshev upper bound probability P of x greater than or equals what? Epsilon. Solution. Okay? What they gave us is this. So our effort first of all is to transform this thing now to look very close to what that inequality is talking about. The moment we transform it, we will not have any problem. How do we transform this? We now come to this. We know that our Chehyshev is what? P of x minus mu greater than or equals what? K is less than or equals what? var of x all over what? K raised to power 2. So let us concentrate on how we can transform this into this. So I will now say, therefore, my P of x greater than or equals what? Epsilon implies P, you open a bracket, you come to this x. Okay? You have what? X minus. You use epsilon here. You see, I brought in epsilon here. Here is my epsilon. So you say what? Minus what? Mu. This is x here. You say minus mu. You come here. Greater than or equal to. Here you have epsilon. You say epsilon minus what? Mu. use it. Here you have P of x minus mu greater than or equals k. Then here you are given P of x greater than or equals what? Epsilon. So you now have it here. We want to transform it to look like this. We are subtracting mu from both sides of x and epsilon. So this minus this greater than or equal to this minus that. So this is looking like this. You now see whether you can transform this that looks into this. Equally transform this to look into this. You now say therefore your P of this of x minus mu greater than or equals to what? Epsilon minus what? Mu. You close it. Is now going to be less than or equals to what? var of x all over. When it was k here, k was squared here. What I have in place of k is this now. So you have what? Epsilon minus mu all raised to power what? 2. And of course, you should note that when x follows an exponential of this parameter 1, the variance is what? Is 1. Okay? Because if it were exponential of lambda, the variance could have a 1 all over lambda raised to power 2. So, but here is 1. If you say 1 all over 1 raised to power 2, it will equally give you 1. So the variance here is what? Is 1. So you now say therefore, P, absolute value of x, mu, greater than or equals to what? Epsilon minus what? Mu is less than or equals to what? var of x all over what? All over epsilon minus mu all raised to power what? 2, which is equals to what? 1 all over epsilon minus mu all raised to power what? 2. So when you solve this, you arrive at this. So this is the upper bound what? Probability of P greater than or equals to what? Epsilon for an exponential of this what? Parameter. There are so many other questions that you can try on your own here, but let us just give you one to try by yourself. So that one is, let me write it here. Let me write it here. Let me write it here as an assignment. Okay, here we have lambda. We have lambda. So, and then the probability that I'm interested in is P of x minus what? E of x greater than or equals what? D. They say where B is greater than 0. So we want you to see if you can get this Chehyshev upper bound for this thing defined this way of an exponential with a parameter lambda. Thank you very much. Stay put as we continue to bring classes for you. Try to drop your comment on your comment section. If you have challenges or if you have questions to ask, put it there. Remember that we owe you to look at the first question which we solved and then come up with a clarification of the answer that we had. Thank you very much.